going to take advantage of Zoom and talk about cosmology. Let me tell you what we're looking at here in these two pieces of art. Uh, this is an astronomical facility. You can get a sense of scale of the facility by looking at this thing here. That's a Caterpillar backhoe to give you a sense of scale. And what we're looking at is something I worked on about 25 years ago that relates to cosmology, and that is the European facility in Chile that includes 4 telescopes. That's these big structures here. Each telescope in this picture has a mirror, 8 meters in diameter, about 25 feet or so. And then these dome structures here are smaller telescopes, and all these can be linked together to do astronomy from the ground. This is one of the things we'll talk about. Here's a side view with the arc of the Milky Way and the large and small Magellanic Clouds. So I just put that in the context of my career. This project was something I worked on in the late 1990s. So let's get started. And yes, I have remembered to turn on the recording. So there'll be a recording of this session available to you and on YouTube. When we're probably in a couple of days or so, you'll get a link showing you how to navigate to this in case you want to watch this again. And there will be, every time I give one of these presentations, there will be a recording. So if you have to miss a session for some reason, or you want to see a part of it over again, those will be available. There's also a link in the chat box. If you go to the chat, you'll see a link to a PDF version of what I'm about to show you. The file I'm working with is a PowerPoint, and it's too big to put in the folder that I have on out on the internet. So this won't, you will, if you use the PDF, you won't see the animation of various lines, such as what's happening now. You will see the videos that I've embedded, but you won't see this, the sequence of introduction of topics the way I just showed it. But you'll have the notes. So here's the structure of the course. Today is lecture 1, of course, and we're going to do what I call the big picture. I'm going to tell you everything that we're going to cover in this class with very little detail, because there's so many technologies and branches of science involved in cosmology that it has worked best for me in the past to gradually introduce topics and use a farming expression. We're going to paint the barn once today, and then we'll go back and put in the details that you really need if you're going to understand the topic of modern cosmology. So not a lot of detail today, but we're going to cover all the topics. And then, as I say, we'll in future lectures, we'll go deeper and deeper into the topic. So the second lecture, that'll be next week, we're going to talk about the early universe, which includes the beginning, the Big Bang, and something that we will talk about a lot, the cosmic microwave background, which is the oldest light that we see from the universe, and it's been a revelation. Once the space-based observation of the cosmic microwave background, the CMB, once that was available, there was an explosion in understanding of the cosmos. And so what I'm going to tell you is the source of information we have is dominated by things like the cosmic microwave background, the big observatory I just showed you, and so forth. All of this has been developed in the last 30 or 40 years. So unless you're a youngster, this has all happened in our lifetime, and we have this astounding new insight into the structure and dynamics of the universe. Third lecture will be about the expanding universe, and the fourth about the dark universe. The dark universe includes dark energy and dark matter, both of which are mysterious properties of the universe. We'll also include in there dark holes, which are black holes, sorry, which are dark objects so dark we can't actually see them directly. We have to rely on other means to see them. The fifth lecture is about the types of signals that we detect using primarily telescopes, but recently the invention of gravitational wave sensors and the use of particle physics, both on the ground and out in space, give us new windows on the universe and its dynamics. And then the last lecture is about new observations, primarily from the James Webb Space Telescope, which has given us lots of new insight, but has created lots of new questions. So that's the structure of the course. Here's a typical slide that you will see. And I just want to point out that in many cases, down at the bottom of the page, there's a panel like this that has additional information. Let me think about, I'm wondering out loud now about whether that's going to work with the PDF version that I've sent you. We'll look into that. Okay. Here's how we deal with questions. I encourage you to ask questions. The best way to convey the question to me is through the chat box, and maybe I will interrupt the flow of the class to answer it in real time. Usually I don't do that. Unless I can see that I can answer the question very concisely, I'm going to carry on with the flow of the presentation. And I will create a question and answer document that I'll share with you after we're done with the session. And we can have that available at the start of the next lecture, the next week, and go into the details. But you can also send me questions at my email, which is down here at the bottom of the screen. I'm happy to get questions like that, but I don't answer them privately. I answer them for the entire class. So keep that in mind. If you have questions that you send directly to me, I'm going to read the question and answer to the entire class. I won't necessarily identify who asked the question, but I don't want people to miss the questions that I get. I want everybody to see every question and every answer. And there's other details here about question and answer. We will have a break so that I can rest my voice after about an hour. And as I said, you'll have access to the lecture notes and the videos. So I've already said most of these things. Now, I will end up repeating myself, and that's entirely consistent with how science evolves. We think we have an understanding of some topic, and then we realize we missed some details or we have to do something over. And so the scientific process I try to illustrate with this piece of artwork is a kind of a zigzag. And frankly, sometimes it goes backwards. We make progress, and then we have new understanding. We have to retrace our steps. So don't be alarmed if I repeat things, because I want to emphasize the topics and add more detail. So I'll introduce topics. I try to remember to explain the terminology at the first time I mention a topic, but occasionally I'll miss doing that, and you should hold me to account if I don't explain a technical term. I generally try to avoid using complex technical terms. I want to use the language we all use every day in explaining this topic. So the goal is at the end of the class, you should understand the content of our universe, the processes that dictate how the universe evolves, the properties of these components, the past properties of the earlier universe, and the likely future of the universe. I'm going to introduce you to the science that underpins our knowledge, which includes primarily physics, chemistry, and a variety of astronomical sciences, and we'll talk about those some today. I will introduce some of the key personalities and the history of their contributions. And as I say, we're talking about progress that primarily has occurred in the last 40 years, principally because of the advance in computing technology, the advances in the physical sciences and mathematics, and the access we now have to space-based telescopes, which we just is a critical part of our resource for discovering properties of the cosmos. In fact, here's an example of what we're getting. This is an image from the James Webb Space Telescope that allows us to see deep in the galactic interiors. Here's the same picture taken from the Hubble Space Telescope, but it's also a stunning picture. But this area here is clouded in the Hubble image with because of the presence of gas and dust deep in this particular galaxy. The James Webb Telescope was designed to be able to get through that dust and see the details. So we've gone from these wonderful pictures from Hubble, and now we have even better pictures from James Webb, and I'll explain to you how you can immediately identify which is which. Oh, and there are links, lots of links to scientific papers and images that you can take advantage of. Click on those to get to the original source. By the way, here's a brand new telescope. This is the Vera Rubin telescope based in Chile. That's the Milky Way galaxy. And we'll talk about the results from Rubin here eventually. So here's a philosophy I have about cosmology. Of course, the universe is gigantic. It's the biggest thing we know of. It encompasses all the galaxies and stars and planets and all the science that we struggle to uncover. And it's, as I write here in this text, one might have concluded at the beginning of this enterprise, back 300 or 400 years ago, when astronomy became a scientific enterprise rather than just people observing lights in the sky, one might have assumed that something this big and complex, such as the cosmos, could never be understood. And in spite of that, over the centuries, we have aggregated our knowledge in the various fields of science. We have technology now for observation. And it turns out we've learned a great deal, again, principally in the last few decades. And we have models for the way the universe performs that match our physical understanding of atomic physics, electromagnetism, the other sciences that are involved. And we've made enormous progress, but by no means are we done. We have unanswered questions, and as I say, lecture 6 the whole lecture will be about recent developments and the challenge we have to understand the universe that's now available to us because of the James Webb Space Telescope and new sensors like gravitational wave sensing technology. So here's a page of information you can go and look at if you need to. It includes some properties of the universe, such as the speed of light, how big a light year is, how big the Milky Way is. I'm not going to go over this. You can read this at your leisure. And because we have to understand the smallest things in the universe in order to understand the dynamics of the cosmos, we'll also occasionally use terms related to tiny numbers as well. I do have a pet peeve. I'll try not to say, when I refer to our planet, I'll try not to say the Earth. We don't say the Mars or the Venus. Earth is the name of our planet. I'll probably slip up, but I try to get people to, sorry, I got my watch is going crazy with messages. We also want to be cautious about talking about the age of the universe. You will soon hear me talking about how old the universe is, and the typical number is about 13.8 billion years. But that could be misleading because we don't know what happened prior to the earliest time we know about, namely the time. What we should be referring to is the time since the Big Bang, which we now embrace as the beginning of our observable universe. The universe could be the result of a prior universe that collapsed and then reemerged in the Big Bang we observe. So it's time to try to clarify the language we use. So we really don't know the age of the universe, but we do know the time since the very beginning of the universe that we observe. And I'll use terms interchangeably, the cosmos, the universe, and so forth. I'll be using both of those. Here's another little table of definitions of tiny numbers. So what are the art forms that we use to observe the cosmos? Astronomy is an ancient art. Thousands of years ago, people out herding their sheep and so forth were out at night and could see the stars, not knowing really what they were looking at. They were looking at planets and stars and galaxies without knowing the difference. Astrophysics is a new development, roughly 100 years old, and it depended on the emergence of the science of quantum mechanics, that is the science of atomic and subatomic physics. And I'll show you a timeline of this, but astrophysics, that is understanding the dynamics of what we observe, such as how the sun produces heat. That could not be explained until, conveniently, quantum mechanics was invented roughly 100 years ago. Nuclear physics also had to be discovered and explained to deal with the physics of what goes on in stars and galaxies. Einstein's theory of relativity, which appears right here, is critical to understanding cosmology. And cosmology is the structure and dynamics of the entire universe. Some people put cosmology as under astronomy, and use astronomy as an overarching name for all the forms of study we do. I don't do it that way. I talk about astronomy as an ancient art. Cosmology is a modern interpretation of what's going on out there in stars and galaxies. And this class is called Modern Cosmology because every time I teach it, I update it with the latest developments. So it's if you see the class I taught maybe 6 or 7 years ago, it's quite a bit different than what you're going to see. And relativity, I've already mentioned, that dictates how space and time evolve in a dynamic universe. So now we're finally ready to start lecture one. And this is a stunning picture we have from Hubble. This picture was taken 30 years ago. Well, not quite 20 years, 24 years ago. This is a picture of a supernova that occurred in 1987, and we see this sort of ring of beads. This is the result of the explosion of a massive star that occurred here, and an outward flow of highly energetic particles and light that interact with the cloud of gas and dust that existed around this star before it exploded. And we now have this much more detailed picture of the same area. This comes from James Webb. This picture was taken in the last 3 years. So let's take a look at how to name the key elements in the cosmos. When we study chemistry, atoms and molecules are the coin of the realm, if you will. In the solar system, planets and comets and asteroids are the things of interest. In cosmology, it's galaxies. And we're going to talk a lot about galaxies, their formation and their dynamics. And we have to, because a tremendous amount about what we know from the universe comes from galaxies and groups of galaxies called galaxy clusters. We'll get into this in more detail. A typical galaxy has around or more than 100 billion stars. And the typical estimate for the number of galaxies in the universe is at least 100 billion galaxies, probably more like 1 trillion galaxies. And from that, we found the following impressive new insights about our universe. The first is the universe is expanding, and its rate of expansion is increasing. And again, I'm just going to give you this as a fact, and then I'll show you the evidence as we progress through the rest of the lectures. Most of the matter and energy is unexplained. The part that we are familiar with, namely the atoms that make up our planet and our bodies, that only represents about 4.5% of the energy in the universe. The rest of the other 95% is unexplained. It is the presence of what is called dark energy and something called dark matter. Those two things, which are describable, but we don't know their origin, that makes up 95% of our universe. The universe has a geometry, and we have various methods for measuring the geometry of the universe, and we find that it is geometrically flat. And we will go into this in a lot more detail. And right now I have to make a distinction between the geometry of something and the shape of something. And we will discuss this later today, but we know that the universe has a flat geometry, but we do not know its shape. So it's a confusing thing, but I'll try to explain it in just a bit. Here's the age of the observable universe, 13.8 billion years. And I've used this term a couple of times already this afternoon, observable universe. That's the only thing we can really talk about. We know the universe that we are in is much larger than the part we can see. This is another perplexing conceptual challenge. We will talk about this. But the observable universe, the one that contains 100 billion stars in each galaxy and at least 100 billion galaxies has existed for around 13.8 billion years. The distance to the most far-reaching object, the distance between the most distant objects, is about 90 billion light years. This is the volume of space that our observable universe contains. And we'll get into this again. I'll show you why we think that's the right number. We do have a major success in understanding where the elements, the atomic elements in the universe came from. And the reason I use the word success is we have to be careful in science to define how we know something is a fact. There are scientific facts. And the only way we can use that term is if we have multiple independent measures of something. If you measure something just once with one technique, you could claim it's a fact, but you run the risk of being incorrect because another measurement might conflict with the one you've made. But our measure of the abundance of all the elements that you learned about when you took chemistry in high school or college, we have factual evidence because we have multiple different ways to make those measurements, and we'll get into those details. And we have new observational techniques. I've mentioned that already a couple of times. We have lots more work to do to understand what we're finding from those new observatories. And they come from gravitational waves, which the first is just the 10th anniversary of the detection of gravitational waves just occurred last month. We have particle physics, and we'll get into that. And we have the cosmic microwave background I've already mentioned. If you want to see some animations that show you the entire universe in just a few minutes, you could click on these movies that are available that show that use a artistic technique to try to capture the size and complexity of the universe. So those, you can click on those and see something we don't have time to go into today. So let's look at the first surprising property of the universe, and that is that the universe is expanding. And we need to be very clear, the universe is not expanding into something. It's not like we are in a beer can that's floating around in a pre-existing volume. It's the volume itself. The universe itself is getting larger, and you might find this confusing. How is it possible that we're in such a situation? And the easiest way to describe this, in fact, the way the professionals speak to each other when they're talking about this topic of expanding universe, is to imagine that we are on the surface of a balloon that is changing size. If you put a bunch of flat creatures on the surface of such a balloon and inflate the balloon, they are in an expanding two-dimensional universe. They can move on that surface. And if they're really two-dimensional creatures, they don't know about up or down. They know forward, backward, left, and right. And perhaps that's our situation, that we're on the surface of a sphere that's expanding. And a balloon of this, if we want to use this analogy, a balloon doesn't have any edges. If you travel long enough in one direction on the surface of a sphere, you come back to where you started. But if your sphere is expanding, even if you travel at the speed of light, you may never come back to the place where you started, because the expansion makes the distance that you have to travel always increasing. There's a property that results from this kind of understanding of our expanding universe, and that is that all the objects around us are receding from us. And roughly 100 years ago, this was a great discovery by Edwin Hubble that distant galaxies are receding from us, and the more distant the galaxy is, the faster it's receding from us. And I will try multiple different ways to show you why this is the case. One of the great discoveries that guides our understanding of the evolution of our expanding universe comes from Isaac Newton 400 years ago, who realized that gravity is affecting all objects all the time. The myth is that he was sitting in the backyard of his family estate in England and witnessed an apple fall from a tree and suddenly realized that happened because gravity tugged on that apple until the stem broke, and the gravity that made that happen, the earth tugging on that apple, is the same physical force that has the earth tugging on the moon and keeping the moon in orbit around our planet. So this is an insight that applies to the entire universe, that gravity is everywhere, working all the time, drawing massive objects together. And we'll see the consequence of that as we work our way through the class. The expanding universe includes these distant objects receding from each other, even though they're connected through gravity. The more distant objects feel so little force from our galaxy and their neighboring galaxies that the expansion of the universe continues to carry the galaxies apart. And we will go through an explanation of why that doesn't affect us. Why doesn't Earth get bigger if the universe is expanding? And the answer is that atomic and gravitational forces for objects near us is so much stronger than the influence that causes the universe to get bigger that our planet is not affected. We are not getting bigger. Our galaxy even is not getting bigger, but the distance to other galaxies is increasing, and we'll get into the details. So I have two illustrations here, an early version of this analogy of galaxies, and many galaxies look like this. Galaxies on the surface of a sphere. As the sphere grows, the galaxies don't get bigger, but they get farther apart. And you can see that as we compare these two images. The second surprise we find as we have a more mature understanding of the universe is that the rate of expansion of our universe has varied over its history. The universe has always been expanding, but the rate of expansion has not been constant. And I'll show you a graph of that in a second. So our observable universe has existed for almost 14 billion years. And for the first half of that 14 billion years, 6.5 billion years or so, the universe was expanding, but the expansion rate was getting smaller. That is, the rate of expansion was slowing. And let me show so in the early days this is the time of the Big Bang, and here we are now at 13.8 billion years. In the early days, the expansion was much, much larger than it is today. But gradually, over time, the gravitational effect in a small universe is dominant. It forces the expansion rate to decrease. So the universe, we now know by looking at galaxies at different ages, the universe had a much larger expansion rate early, and that expansion rate gradually fell, but at all that time, initially small effect, namely the effect of dark energy, was inconsequential early on, but it was persistent. And right here, about 7 billion years after the Big Bang, the influence of dark energy compelling the universe to get larger overwhelmed the gravitational effect. And we now see that we are in an expanding universe. And the best information we have now is that expansion will continue forever. So this is our first encounter with this mysterious dark energy. Has this overwhelming influence now that is causing the universe to expand, but we don't understand where it comes from, why it exists. And we'll talk about some theories of why dark energy exists, but its influence is unavoidable. We are now in a phase of the universe where the expansion is accelerating, and that's a new discovery as of roughly 1998. So, less than 30 years ago, this was a discovery that shocked everybody. So what we have here on the graph is two competing factors: an expanding universe where initially gravitational forces were dominant, and now the influence of dark energy is dominant. And so we actually went through a minimum in the expansion rate about 7 billion years ago. Now, I mentioned the universe has a flat geometry. We have multiple ways to detect this. What I mean by that is if you went out in space with a giant ruler and a protractor and the other compass, like all those things you used when you took geometry in high school, and you measured the properties of triangles, for example, you would find that a triangle drawn in space has 180 degrees in its three angles. If you measured the properties of parallel lines, if you projected two laser beams, for example, and followed them forever, you'd find they never cross. That is a property of plane geometry or flat geometry. The ancient Greeks invented understood the properties of plane geometry, and that's how our universe behaves. But we have to make a distinction. We know it's geometry, but we don't know its shape. And I'm going to show you an example of how this can happen. What are the properties of a flat geometry? Well, I mentioned two of them. Triangles have 180 degrees. A circle has a circumference of 2 pi times the radius. Parallel lines don't cross, and so forth. So this is something you saw when you took geometry, properties of lines and triangles and circles. Now, how could it be that the shape is not flat? Let me give you an example. This is part of a sewing pattern my wife loaned to me. It has angles and lines and so forth. If I take this sheet of paper and put it back in the wrapper that it was in when she bought it, you see that it's rolled up. The angles, for example, right here, there's an angle between two lines, a right angle. If you measure that and make it part of a triangle, you'll find that 180 degrees describes a triangle drawn on a flat sheet of paper, even if you roll it up. So this is an example of a flat geometry that doesn't have a flat shape. And the actual shape of our universe is in that form. The detailed properties of the shape are unknown, and there's some question about whether we will ever find out the shape of the universe, principally because we can't go everywhere in the universe and make measurements that as well as we can if we are just dealing with paper rolled up and so forth. if you click here, you'll see an article in a scientific magazine that shows you some possible shapes for the universe. Here's surprise number 4. I mentioned that we know the origin of the elements that come from what is called nucleosynthesis. Here's the periodic table you saw when you of elements you saw when you were a student. And all the elements are here, including the ones that are artificially created by humans in reactors and so forth. We now know that 99% of all the matter in the universe is captured in the form of hydrogen and helium. And the way this is laid out, it's anything that was produced in the Big Bang is this blue color, and then the rest are almost all related to the behavior of stars, elements created in stars. For example, here's aluminum. Almost all of it was produced in exploding massive stars. So the periodic table that we have here showing that molybdenum principally came from low mass stars exploding and merging neutron stars. And we'll explain what a neutron star is in good time. So we have this depiction of the origin of all the elements, and we've measured the amount of all these elements by looking at galaxies using techniques I will explain. But virtually the entire universe is either hydrogen or helium. And as I said, even if you take all of that, all these elements put together only represents 5% of the energy in the universe. The rest of it is the mysterious dark energy that I've mentioned and dark matter, which we haven't talked about yet. Here's the pie chart of the different kinds of energy that exists in the universe. I should have mentioned, of course, that when we rely on Einstein's insight that energy and mass are related, E equals mc squared is, in every school in the world, written on somebody's wall in the physics room or the chemistry room. So here's the partition of energy in our universe. And we have multiple ways to measure this. So we call this factual because we can confirm these numbers as properties of our universe. The blue segment, the biggest one, is dark energy. Roughly 70% of all the energy in the universe is dark energy. Dark matter takes up a huge sector, 25%. Right here is hydrogen and helium that's not in the form of stars. It's just gas floating around. And this little green wedge here is the fraction of energy in the universe made up by stars. This whole thing, this sector here, that's all atoms, that's 5%. So here's the data supporting that. And that's recent. Recent insights give us this version of the partition of different forms of energy in the universe. And we are a tiny, tiny part. Let's talk about the size of the universe. One of the things we know is that the most distant objects in our observable universe are about 45 billion light years away from us, in spite of the fact that the universe is less than 13 billion or 14 billion years old, because the expansion of the universe has carried objects away from us at speeds greater than the speed of light. And we'll explain how that can happen. The most distant objects are about 45 billion light years away. So if you were on one side of the universe and looked back to us and then looked at the most distant thing beyond us, that means the universe is about 90 billion light years. It's a volume characterized by a distance of about 90 billion light years. And we also know that that's our observable universe. And because of the expansion of the universe and the extremely high expansion rate in the early universe, we know that this volume, this 90 billion light year volume that I'm talking about here is only a part of a much bigger universe, part of which we cannot see and we will never see because the light from that much larger space, even if it's coming toward us, it will never get to us because the universe continues to expand while the light is propagating toward us. So the working dimension that we always talk about is that the most distant objects are 45 billion light years away. And I've included here an image of how the expansion of the universe, if you click on this, it puts you into YouTube, you'll see the interaction of galaxies that might have occurred during the expansion of the universe. One of the things we can anticipate is because the universe continues to expand at an ever-increasing rate, far, far in the future, say 100 billion years from now, scientists or citizens on a future version of Earth will not know about other galaxies because they will all have receded from us and disappeared. So this is a good time to be taking this class because in the far future, there will be no discussion about distant galaxies because scientists will not be able to detect them. Here's how your body is made up of the star stuff that comes from exploding stars. Here it is by a percentage. So most of your body is oxygen, it's carbon, hydrogen, and so forth. And here's the stellar events that created these elements. White dwarfs, or exploding white dwarfs, we'll discuss this more. The original Big Bang, that's the hydrogen and helium, mostly hydrogen. There's very little helium in your body. Dying low mass stars and exploding massive stars. So we are star stuff. And so here's what we know. The universe is expanding at an ever-increasing rate. Only about 5% of the universe is atomic. The rest of it is stuff we don't understand. The universe is flat, geometrically flat, and has some unknown shape. It's been around for almost 14 billion years. All of the entire cosmos we're talking about is embedded in a volume with a diameter, if you want to use that term, a space 90 billion light years across. And we understand the evolution of the elements in the early universe. So let's jump into a little history. This is a nice graph, but it happens to be a little different than most. Here's 1500, and here we are today in 2025. And these are the key players who were involved in originally astronomy and then eventually the application of physical science, physics, chemistry, mathematics, to observations made on crude telescopes dating back to the 1600s. So you see 1600, 1700, 1800, and so forth. And all of this, through this whole span of time, even going back to prehistoric times, is what I've called here observational astronomy. Just noticing things in the sky and wondering what they were and what they were doing. The invention of relativity from Einstein dates back to 1905. That's a key scientific tool we need to understand the cosmos. Quantum mechanics, that is the study of the subatomic world, was invented virtually the same time as relativity. Those two together led to astrophysics, where we now have the tools to understand why stars and galaxies behave as they do. Einstein's second great contribution is his theory of gravity, which we will hear lots about in the coming lectures. That occurred around 1917. So these are the tools that converted observational astronomy into what we now call cosmology or astrophysics. Here's an example of what was going on before the application of the sciences, just observational tools. This is Messier, a French astronomer, who observed the sky from a small telescope in downtown Paris. In his day, in the 1700s, there was no light pollution from street lights and cars and so forth. And his view of the sky was unobstructed, even though he had a very tiny telescope, I think about 4 inches in diameter. He drew this picture of our neighboring galaxy, Andromeda. And here's a modern picture taken by the Hubble Space Telescope of Andromeda. You see it's a great spiral. Our galaxy looks very much like this. And it has neighbors, these small mini galaxies that are attached to it by gravity. And so you can see here, he drew this, which is that, and he drew this, which is that. And he, over a period of time, drew the best images he could of what he saw with his tiny telescope. This is called the Messier Catalog, and it includes 110 different lights in the sky we now call galaxies. And you'll see here, some are spirals, some are seen by the edge where we don't see the structure. Some are seen M50. Well, it's the title here is blocking my view, but there's all kinds of galaxies. And Einstein, in the early 20th century, introduced his ideas about gravity and the way it interacts with, it causes space and time to interact with matter. And in his day, in the early 1900s, or up to about 1920, the assumption was the universe had existed forever and was unchanging. And Einstein had developed these equations describing how gravity dictates the evolution of the universe, and had to do some contortions in the math to make sure that the results of his calculation produced a result that showed a static universe, because that's what all the astronomers told him. The universe is static. But his equations then got investigated in detail by Alexander Friedmann, possibly a neighbor, a relative of mine, although I don't think so, and a Belgian priest, Lemaitre. They took his equations and studied them in detail and discovered that his equations predicted the possibility of a dynamic universe, one that could grow or get smaller. And very quickly challenged this idea of a static universe. But they needed evidence to determine if you go outside night after night and look at the lights in the sky, you're not going to detect this with your eye. And there's Lemaitre and Friedmann, and they sort of an accident of nature. Edwin Hubble, at the same time in the 1920s, was measuring properties of galaxies. He was measuring the colors of galaxies, and we'll get into something he used called redshift to determine that all the galaxies he saw through his much bigger telescope than Lemaitre show the galaxies were receding from him. And what allows us to detect that is a receding object is seen with color shift, namely redshift, if it's going away from you. So if you measure, for example, hydrogen in a laboratory, you see it has certain, like a fingerprint, these dark lines. We'll discuss these in more detail. And then you look at hydrogen in a distant galaxy, you see the same lines, the same fingerprint, but shifted. And that shift is the result of the fact that the light source producing what you detect from a distant galaxy is moving away from you. And Friedmann and Lemaitre used the ideas of Einstein's theory along with the results Hubble had been producing, and showed that we could be living in a universe that has been expanding and will decelerate and have a big crunch, or one that keeps getting bigger. And it turns out none of this is right. We're in this kind of a universe, that this rectangle depicts where we are now, and the spacing of the galaxies is always going to keep increasing. Einstein's equations predict that. So for a long time, there was, for about 20 years, there was progress in understanding how the universe might evolve, and then World War II got in the way, and Europe was where much of the work was being done, was, of course, completely disrupted by the war. A lot of scientists went into war work. They fled the European area. And so there was a delay in progress. And after the war, this idea of a static universe still persisted. A small number of influential astronomers still argued that the universe was static, in spite of the work of Lemaître and Friedman. And it wasn't until the late 1940s when George Gamow, who has a building named for him at the University of Colorado in Boulder, he and his students predicted something called the cosmic microwave background. That is, afterglow from the beginning of our universe. And new technologies, many of which derive from military technology, had emerged. Electronics, computers, understanding nuclear physics, rockets and space telescopes all became available. And great progress was made. Let's quickly cover a topic we're not going to emphasize in this class, and that is we're focusing on cosmology. So we're not going to talk very much about planets, moons, and individual stars. I'll just say that here's our solar system made up this way. There is a way to classify different kinds of stars. We will touch on this a little bit, where our sun is one of the stars on this chart, which depicts the temperature and the brightness of the star. And we'll talk about that, not a great deal. Here's our solar system, where these rings represent the orbits of the planets. There's Pluto, no longer considered a planet. Outside of Pluto is a cloud of ice and comets and dust called the Kuiper Belt. And outside of that, if we take this whole drawing here and put it in this little tiny box, outside of that, there's the Oort cloud, just dormant, cold region around our solar system, around our sun, that occasionally delivers a comet or asteroid into the solar system. So we have some understanding of this. I'll let you read this at your leisure. Typically, astronomy books say that our sun is typical. It is not typical. Here's a picture of it taken during the eclipse of 2017. Many of you probably witnessed that eclipse. My grandson took this picture, and you can actually see sunspots and the disk of the moon as it crossed the sun. But our sun is not typical, and here's some examples of that. Here's the production rate of stars in our universe. Dating back to the early universe, star production was very low because the work of gravity to draw clouds of gas together to form stars had not really been very influential, but gradually the star production rate increased and maximized after about 3.5 billion years of the universe. And by then, stars were forming, and galaxies were forming, and the rate of production of stars started fading away because most of the gas you need for stars, namely the hydrogen, was already in stars. And the expanding universe was separating the galaxies. So that was the influence of gravity was getting smaller. So this is a model of the production rate of stars over the life of the universe. Here we are today. Here's actual data that shows confirmation of this model. And here's where we're going to stop in a minute because we're going to take a break. But here's our Milky Way galaxy. Now, we cannot take a picture of the Milky Way. It's because we're embedded in it, we can't see the whole thing, but we can measure the motion of stars in the Milky Way, and we can construct what it would look like if we could get outside of it and take a picture. And this is what it looks like. It's what is called a barred spiral. And we'll see why the term barred is used. It's a typical galaxy, has this spiral result, probably because of ancient collisions between galaxies that typically produces these spiral arms. Here's our sun, kind of halfway out in the galaxy, and you can see various measures. It's about 200,000 light years across the galaxy. Our neighboring star cluster group is here. Here's the sun, and there's a group of 20 or so stars within 10 light years of our star. Again, here's what our galaxy looks like. There's the sun. And our last slide before the break, I already mentioned this. There are at least 100 billion galaxies in the universe, each with about 100 billion stars. So here's some examples of galaxies taken by modern telescopes. You see the spiral structures. All right, so let's take a break for 5 minutes or so because we have lots more to talk about. And so I'm going to go on mute and I'll be back at 2:08 according to the time standard that exists in Fort Collins. Okay, folks, I'm back. It's 2:08. And thank you to Craig, who asked a question. He asked me, what is a GYR? And that stands for giga years, an abbreviation for billions of years. So everybody, please do this. If I use a term and or have a term on the screen that I don't define, let me know and I will uh, clear it up as quickly as I can. So let's go on and finish our discussion of classifications of galaxies. And you see samples here. This is an organization of taxonomy of galaxies organized by Edwin Hubble during his studies of galaxies in the 1920s and 30s. He's got elliptical galaxies, and you see samples here are examples. And then spiral galaxies that have these wonderful spiral arms, probably as the result of collisions between galaxies. And then you have the so-called barred spirals. And you see why they have this name. It's a spiral, but it's got a roughly straight line of bright stars across the center. Here's Hubble in the Palomar telescope that he used so frequently. And modern day telescopes and systems, of course, rely on organizing data using computers and keeping track of the positions of the millions of galaxies. And we have the result of images like this. This is a picture where every dot here is a galaxy. This is a recent thing, probably done in the last, starting in like 2015 or so pretty recent. And I'll show you the scale of this in a second. But you see the structure that we're now able to see by using modern telescope technology. Uh, Once again, we get the velocity of how each of these galaxies is receding from us. And by using a technique that I'll show you in a minute, we get the distance to these objects. So we have lots of knowledge of each of these hundreds of thousands of galaxies that make up this particular image. And here we are. Here our telescope is here. This reaches back into the ancient universe in distance, 2 billion light years. Remember, I said the universe is the most distant object from us is 45 billion light years away. This means that this image, this wonderful image, is only sampling a small part of the universe. The volume that you have to deal with when you're doing astronomy, galactic astronomy, is enormous. But we have this, it shows us dynamics that has gravitational dynamics that cause these clusters of galaxies to form, and we get these things that are called walls, where you have, and the color is indicative too. The redder the dot, the older the stars in the galaxy. And here's a nearby picture. This is the supercluster that our galaxy is part of. It's Laniakea, and it's 500 million light years across. And here's a book that dates back 30 years, but still is pretty much on target, about the Great Attractor. That is this point right here, where there's a flow of galaxies toward that point, all the result of gravitational influence, and we are located here. Here's a nice piece of artwork you can find on Wikipedia. Here's our solar system. There's the sun, the planets, asteroids and stuff. The Milky Way galaxy around us, other nearby galaxies here, and way out, 45 billion light years away, is the source of the oldest light in the universe, namely the cosmic microwave background. So I'm using that term. We will talk about what it means, but you should get comfortable with that term, the cosmic microwave background. I'm going to skim through this because we have lots of topics to discuss today. But here's Andromeda, our neighbor. I already showed you this. This object rotates in around 250 million years. Let's see if I got that right. 2.5 million light years away. And this galaxy and our Milky Way galaxy will merge eventually. And you see how many stars are in this galaxy. 1.2 trillion times the mass of the sun. This is a symbol. We'll use this occasionally. This symbol represents our sun. And here's some typical galaxies. This one is a cluster, and this group of bright objects is the inspiration for the thing on your car if you own a Subaru. The Subaru in Japanese refers to what we call Pleiades. So different kinds of galaxies, and we'll get into some of the details. Here's a model of the evolution of galaxies from the Big Bang. Clouds of gas and dust collecting to form stars, and then the stars getting bound together gravitationally to form a galaxy. And in some cases, the galaxy has, well, in virtually every case, galaxy has a supermassive black hole in its center. We'll get into more details about that. Now, let me take a break here just to make sure that if people have questions, unmute yourself. I've been talking for 1 hour and 15 minutes. If you have questions, unmute yourself and pose a question, or you can put something in the chat and I'll read it and respond to it after we're done today. Okay, there's no questions, we'll carry on. So there's more detail here you can read about the evolution of galaxies and galaxy clusters. Here's yet another way to observe this. This is a computer simulation where we have essentially a uniform distribution of little dots in a box in a computer simulation. Each dot represents a galaxy. And the placement of these things is kind of random, but overall, it's a uniform cloud or gas, each dot representing a galaxy. And then time progresses this way from here to here to here. And you can see these clusters forming to here, to here, to here, and so forth. And eventually, all the structure is built in to this simulation of the evolution of positions of galaxies in the universe. And so you don't see much change from here to here to here. So computer simulations are now a powerful tool in how the universe has evolved. And here's the dates after the Big Bang. So early on, and here we are now. Viewing perspective is beyond our control. So we have some fortunate cases like Messier 51. Here's a spiral galaxy drawing matter from an object nearby, dragging that mass and gas and dust and stars into this galaxy. And this one we have a side-on view, so we can see the spiral structure. If we look at this one, we're just looking at it's like looking at the edge of a plate. We can't see this structure, but we can see this dense area of gas and dust where stars are forming. So different views. Now, one of the most interesting views we have of galaxies comes from a process that predicted by Einstein. He never thought it would be observable, but indeed it is. If we look at this spot on the sky, this is called the Einstein cross, and you can get more information about it clicking here. But what's going on here? In the center, we're seeing a faint glow of a very distant, extremely bright galaxy. This is one of the so-called quasars, a quasi-stellar object. This was a mystery for a long, long time, but in the late 1960s, people finally realized that galaxies almost always have a black hole in their interior, right in the center where the galaxy is brightest. And if the black hole has enough debris in the form of stars and gas and dust to keep it active, consuming that material, it produces a prodigious amounts of energy. And the light from this quasar, which dates back to the very early time in our universe, is so bright that we can detect it with our telescopes today. And the question is, why do we see 4 dots? And the reason is, here's the quasar way off in the ancient past. And here's an intervening galaxy that has a collection of matter swirling around. It's a galaxy or group of galaxies. And that matter influences the trajectory of the light rays coming from that ancient quasar. And by the way, that quasar may not exist anymore. It might be so old that it has consumed that the black hole consumed all the fuel available for it to consume and just goes dark. And a black hole is indeed, it's dark. You can't see it. The radiation from that time when it was active is still propagating toward us. And if an intervening galaxy is aligned just right, we see multiple images of this object. That's what's happening here. The quasar, the light from the quasar gets deflected to our telescope here at Earth. And so we have now, because we have these wonderfully capable space telescopes, we can see these kind of objects all over the sky. And they're very useful scientifically. I'll explain that eventually. So this light all comes from a supermassive black hole digesting everything around it. And the supermassive black hole typically is measured in at least millions and sometimes billions of solar masses. That is, it would take billions of our sun to create the same kind of effect. So we have hundreds and hundreds of these, millions of these quasar objects. And in some cases, the alignment is just right. So we see these mirages. Now, how do we know that each of these 4 bright spots that are shown here, how do we know that they're all coming from this quasar? And the answer is we measure the redshift of each. Remember, that's the influence of the velocity of that object away from us and how it shifts the color of light that we detect. And because the quasar is carried away from us by the expansion of the universe, if we measure the redshift of each of these spots, we discover it's exactly the same redshift. In addition, the details in this light can be used to look at the chemistry of the galaxy in which this quasar was embedded. And we match those and we find the same chemistry. And the third thing is the black hole in this quasar doesn't have constant output. If some large amount of gas or dust wanders into the neighborhood of the black hole, that gas and dust gets into orbit around the black hole before it's consumed and gets heated to enormous temperatures, becomes very bright, and radiates that light all over the universe. But the amount falling into the black hole at any one time is always changing. So we can look at the changing brightness of these 4 spots. And if the redshift and the chemistry and the output, the energy output in each of these is the same, we can presume it all came from light from one single object. Here's a case where the intervening galaxy had a nice kind of round symmetry. So we see what's called an Einstein ring instead of these spots. Now, I've mentioned redshift. It's time to dig in a little bit into why we can detect that. So here's the electromagnetic spectrum that includes radio, television, microwaves, and a little sliver of light that our eyes are able to see. And it has the colors you're familiar with. Here's how light from the universe gets to us. It depends on the transparency of the atmosphere of Earth. We see the colors coming from the sun because the atmosphere above us is transparent in the colors that we have evolved to be sensitive to. In other parts of the spectrum, like gamma rays and X-rays, none of the light out in the universe gets to the ground. The same is true for certain kinds of infrared, that is heat, the light associated with heat radiation. So we have evolved to be sensitive to the part of the solar light that reaches the ground. But the universe is filled with all kinds of other signals. Fortunately, radio waves can get all the way to the ground, so we have radio telescopes. We don't have to build a space-based radio telescope. We can build them on the ground where it's much cheaper to create that kind of technology. Here's that observatory I worked on down in Chile. And to make a successful investment in such a thing, and this is a roughly $1 billion investment the Europeans made, you go to places that have the right kind of weather, that is infrequent cloud cover at high altitude and stable wind. And this observatory is in such a place in the desert in Chile. You can see there's nothing green growing around here. It's high altitude and very dry. Here's probably the premier spot in the world for ground-based telescopes, and that's on the Big Island of Hawaii, on the dormant volcano Mauna Kea. And you see gigantic telescopes there. Here's my wife and I at the summit of Mauna Kea. Of course, when we can afford it, we build space telescopes. Here's the Hubble Space Telescope. And of course, now we have the James Webb Space Telescope that's in its third year of operation. The reason that we can detect the redshift I've talked about is we take advantage of the spectra that is in light. So you can do this. You probably have done this. So you can take a prism and shine light through it. Just look at the sun or something, and with being careful not to hurt yourself, you could see the different colors because the prism spreads out those colors. You can do it. Here's an example where you have a bright light on a prism and you see the rainbow of colors. But when you look in a scientific sense at that spectrum, you can see the presence of different kinds of absorption lines. If you look closely, you'll see these dark lines. They indicate the chemistry of what's in the atmosphere of the star that produced these various kinds of examples. Each of these is a different kind of star. Our sun is a G star, and it has a variety of chemicals in its outer most surface that absorbs light and re-radiates light. So we can detect the chemistry of things, but also we can see the redshift because the lines are shifted in relative to what you would find in a laboratory. So if you look at hydrogen in a laboratory, you get these lines. If you look at hydrogen in a distant galaxy, you see the same spacing, but a shift indicating the velocity at which the object's receding from us. The redshift has its, you've all experienced the Doppler shift, which is an acoustic effect where an ambulance or a train or something going by you, the siren changes pitch as it goes by you because the object is on a moving platform. And Doppler first noticed this in the mid-1800s when you could have something going fast for the first time, probably a train with a whistle. People began to notice, oh, there's this so-called Doppler shift that's an acoustic effect. And the same thing happens in electromagnetic radiation from stars and galaxies. And so roughly 100 years ago, early modern astronomers started using this to get the speed of objects in the sky receding from or approaching us. And in the case of where they're approaching us, we have what is called a blue shift. So here's hydrogen emission. So if you heat up a container, a cylinder of hydrogen, you see these emission lines. If you use a light source and put cold hydrogen in front of it, then you see the hydrogen absorbing at exactly these frequencies, or these wavelengths, or colors. And that's because hydrogen has a certain structure which was unexplained until roughly 100 years ago when quantum mechanics became a mature science. This effect had been observed for 100 years or so in the 19th and early 20th century with no explanation until the structure of the hydrogen atom was properly explained by quantum physics. So here's an example of a galaxy, various galaxies that have hydrogen or oxygen. And if the galaxy, we'll talk about what Z means eventually, but not right now. If we look at a galaxy moving away from us at a relatively low speed, we see this structure. It's a fingerprint that's easy to recognize. And here is where it is in the color spectrum. And there's a corresponding peak here. If we look at a different galaxy moving away from us at a higher speed, we see this structure shifted. And a higher speed, it's over here. All these shifts are going toward the red. And for the biggest shifts, the spectrum is no longer in the visible range of the human eye. It's in what's called the infrared spectrum. So modern space telescopes, particularly the James Webb Space Telescope, was designed to work primarily in the infrared spectrum. It does some visible, it can see some visible light, but it's designed to see highly redshifted objects, which means the oldest objects moving away from us at the highest speeds. And that's what Z indicates. The redshift tells us the amount of the Z number tells us the amount of redshift. You see these are successively larger, and you can see the spectral shift here. So a large Z indicates how fast an object is moving away. And because we have what we think is a reliable model of the expansion of the universe, if we know the velocity, then we know the current distance to that object. And so on some of these graphs, I've added that information. So quasars, I've already described what a quasar is. Here's that drawing I showed you before, the so-called Einstein cross. There it is. And here's how the redshift of a distant galaxy or quasar is characterized. There's the redshift Z equal to 0.178, and we see that's a structure associated with hydrogen. At the higher Z, we see more shift and so forth. And now, just as an example, this galaxy, PKS 1217, has these properties. It has a Z of 0.24, which means the light we now detect from it was produced about 3 billion years ago. There's that giga years that I failed to define in the first hour, that it's the distance to that object now, if you could see both us and that object at the same time, you'd find it's about just over 3 billion light years from us. And it's moving away from us at about 25% the speed of light. So this is what we derive from the Z value. And I'll show you examples as we go along of how Z works. Now, so far, all I've talked about is the speed of the objects receding from us. A critical thing we'd like to know is the distance to the object. And it turns out that getting the speed is easy. We use the redshift to do that. But getting the distance to a distant object is hard. And let me show you how we've developed a scheme for dealing with this. What you need to get the distance to an object is some measure of brightness of some kind of an object that we understand. And the object that's most important to us in understanding how to get distance is a so-called Cepheid variable star. Here's an example of a Cepheid variable. You see the calendar dates here over about a year. These stars get brighter and dimmer because they swell up and then they collapse, and they swell up and they collapse. And we have Cepheid variable stars near us in the Milky Way. And a pioneering astronomer, I'll introduce in a minute, figured out that if we look at the Cepheid variable stars near us in the Milky Way, if we had a way to measure the distance to those variable stars near us, then we could get a sense of how far away these Cepheid variables are in much more distant objects, like in distant galaxies. And in the early 20th century, that's what was accomplished. So how do we get a distance for a Cepheid variable near us in the Milky Way? And the way we do it is shown here. This is an animation, and let me talk about it first, and then we'll animate it. The way we do the distance to nearby objects is make a measurement of the star with other stars in the background. Stars are galaxies that are far, far away. And then when you wait 6 months, now Earth has moved to the other side of the sun, has moved halfway around the sun. And now take a picture of the same object with a different set of background objects. And you can do a little arithmetic and figure out the distance to the Cepheid variable. And we used to be limited in doing this kind of thing, looking at objects near us in the Milky Way galaxy. We now have much more capable telescopes, namely space telescopes, and we can use this technique. It's called parallax. And so let me now start the animation. So here's Earth going around the sun, and we're seeing the apparent position of this Cepheid variable against the background of very distant light sources. Now we can do it for Cepheid variables that are much farther away. But in doing this, we can characterize the light output from these Cepheid variables, because we know the nearby ones rise and fall in light output proportionate to the period of their brightening and dimming. In this case, this object brightens and dims in about a month. So using this, we get what's called a standard candle. We can tell that the Cepheid variable near us, the distance to that is known using parallax. Then we can see the similar kind of Cepheid variable in another galaxy and look for typical variable stars, and that gives us the distance. Let me give you this example as a way to think about it. Tonight, you could go outside and look at the brightness of a headlight of one of your cars and get a sense, maybe take a photograph of it or something, get a sense of the brightness of that headlight when you're standing next to it. And then have somebody drive that car a mile away and measure the brightness of the headlamp from a mile away. Now, the brightness of the lamp didn't change, but because it's farther away from you, you can draw a conclusion about how far away it is by looking at how much dimmer it is. And that's what we're doing with these Cepheid variable objects. So using Cepheid variables, we can get the distance to nearby galaxies. The next step is we want to reach way out into the universe. How do we do that? And the answer is we look for supernova events of a particular kind called type 1a supernova. And these events are rare, but when they occur, they last for maybe 2 weeks of brightening and dimming. We'll see much more detail about this in a future lecture. But if we can find a Cepheid variable in the galaxy in which the supernova event occurred, and we know the distance to the variable star, now we know the distance to the type 1a supernova. And we understand now, with modern nuclear physics, we understand what goes on in supernova events to cause the amount of power they put out. And the type 1As all have the same power output. They all have the same chemistry. And when they explode, they produce the same amount of output power. And by measuring that output power, we can get the distance to the galaxy they're embedded in. So it's a long, complicated thing. There's much more to it, of course, but it's a long, complicated thing to figure out how to find the distance to distant stars or galaxies. Getting the velocity is easy using redshift. You can see these things flashing every once in a while. Those are supernova events. They occur about once per galaxy in 100 years. I don't know if that's right, but it's a rare event. But if you're looking at millions of galaxies, you're going to see supernova events all the time. Here's the hardworking astronomer who invented the Cepheid variable technique. That's Henrietta Leavitt. And we now know, for example, we know the distance to these companions to the Milky Way, the large and small Magellanic Clouds, because there are Cepheid variable stars in there that are close enough that we can use the parallax technique. And this is the kind of thing we're talking about. The period of variability of the star is related to its brightness as it gets brighter and dimmer. And we can plot that. And here are the Cepheid, these yellow dots are the variable stars near us in the Milky Way. And here are the stars in the large Magellanic Cloud, that's this one, only visible in the southern hemisphere. And you can plot a line here, and this line is getting better and better all the time as we have newer space telescopes. So in summary, we can do radio astronomy. Here's a picture of a galaxy in radio, the same galaxy in the infrared spectrum. Here it is as it looks in the optical spectrum, ultraviolet and X-rays. And you can see, for example, regions of star formation here where the X-ray spectrum is so bright. There are spots in this galaxy that just stand out as locations where star formation is most prevalent. Here's this looking at outward at the Milky Way. Here's radio, hydrogen, molecular hydrogen, the infrared, and so forth. This is what the Milky Way looks. This is what you see if you go to out in the desert at night or any dark spot out in the ocean. This is what you see in the optical spectrum looking at the Milky Way. So having all this kind of technology available got us to the point where we discovered the expansion of the universe, because Hubble detected the redshift associated with distant galaxies and was actually the first to promote the idea that the lights in the sky were not all close to us. Some of them were. I mean, some are planets, but some are stars in the Milky Way. But a lot of the light you see in the sky are galaxies, and they're moving away from us. And Hubble analyzed the data and produced the result that not even Einstein had imagined, and that is the universe is expanding. So we have the cosmological principle that says the average density of galaxies in the universe is the same everywhere. This is an unproven assertion, but it seems to work. And it also, part of the cosmological principle is if you go to any spot in the universe, no matter which direction you look, if you look at a big enough volume, you'll see the same density of galaxies no matter which direction you look. This is called being isotropic. So we have the density of galaxies asserted to be the same on a large scale. Let's say hundreds of millions of light years. The same density, no matter where you make that measurement. And again, this has seemed to work. We don't have a special place in the universe because the expansion of the universe is observed by all observers. No matter where you are, you see everything moving away from you because the universe itself is getting bigger and the space between the galaxies is getting bigger all the time. Check something real quick. So we don't have a special observing place. Humans are not at the, in the center of anything. We're just average observers seeing hundreds of billions of galaxies, and any other observer in the universe is going to have the same experience. The cosmic microwave background, which is the heat radiation left over from the Big Bang, looks a little different for everybody, but basically it's the same no matter where you are in the universe, and it's an enormous source of information for us. So here's a typical model. This has been around for 25 years. It comes from NASA, that the universe began, we don't know why, with an explosion into existence of an enormously hot, small collection of radiation. And over time, that radiation cooled enough that particles formed, and eventually atoms started forming. Because if you put an atom in an extremely hot environment, the intensity of the light will break the atom apart. It will ionize the atom. So in the early universe, atoms could not exist. It took about 400,000 years before the temperature in the universe dropped to a point where hydrogen could form. That is, where protons and electrons merged together to produce hydrogen. At that point, the universe became transparent. Now, there were no stars, so it was total darkness. Just atoms of hydrogen flying around at enormously high speeds, bathed in the radiation left over from the Big Bang. And it took 400 million years. Now, I'm going to amend this in a second, but on this drawing, it says it took 400 million years for the first stars to form. And that was true when this piece of art was developed 25 years ago. We now have a different view, and the James Webb Space Telescope is informing us with more data every day that this number is way too big. The stars started forming maybe around 250 million years after the Big Bang. Why did we have stars forming? Because of gravity. Clouds of hydrogen would be attracted to each other by the gravitational force. Eventually, if you get enough hydrogen into a one small space, it will get hot enough at the center of the cloud to create nuclear fusion, and you start producing the heavier elements, namely helium. And so the formation of stars took a while, but we had this long period of darkness in a transparent universe. And once you have stars, the stars notice each other through gravity, and you form galaxies. And the galaxies might even notice nearby galaxies through gravity and form galaxy clusters. And then after a billion years, then you have an evolving but relatively stable universe with galaxies, galaxy clusters, and the chemical composition that we observe today. So that's what happened in this drawing. And the only thing that's really changed since this drawing was first made is this number, 400. It's probably more like 250 or something like that. Now let's talk about how do we interpret expansion? If you're standing on a shore and a boat goes by you, you have a couple of different ways to interpret why the boat is moving past you. One is that the water is moving, that it's being carried along in the water. And another is that it has some kind of propulsion, that somebody's rowing the boat, or it could be a combination of the two. Modern way to think about the way expansion of the universe goes is that the things we see, in the case of the boat, we're going to replace that with a galaxy. It's moving because the distance between galaxies is getting bigger all the time because of the expansion of the universe. So there's some detail here you can read. There's a funny clip in this you can find here about this child, a young Woody Allen portrayed here, who goes to the doctor. His mother drags him to the doctor because he doesn't want to do his homework. He thinks that the universe is expanding and it will eventually explode, and why should he bother doing his homework? And technically, the explanation that the kid provides is actually correct. It's amusing. Here's that expansion thing I talked about before. Maybe we're on the surface of a expanding sphere, a sphere in a dimensional space that we do not experience. We're not sure. So Hubble in the 1920s estimated the expansion rate of the universe by measuring the recession velocity of galaxies, and his numbers were here. These are the velocities that he estimated. The problem was that his estimate of distance was way, way off. And you can see why. It's a complicated thing to develop a methodology for getting the distance correct. He had the velocities correctly, but the distance is hard. And so what's happened over the last 100 years is the value of the expansion rate, which is called the Hubble constant, has drifted down, 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 and we now have a good but not great estimate of the Hubble constant. In fact, we have a problem because as we use different methods to measure the Hubble expansion rate, we get different values This was not expected. It became a problem about 10 years ago, and everybody is struggling to understand why we can't get the three key methods for measuring the expansion rate to agree. And they're radically different. They're about 10% different, which is perturbing everybody. So we won't go into this here, except to say Hubble's value for the expansion rate was like this. We now know it's like this, but it's somewhere in this yellow wedge. We just don't know it well enough. It's getting better. Here's a comparison between the best data we had from Hubble and the best data we have from James Webb Telescope. And you can see that this is the Cepheid variable data that I showed you before, but you can see the scatter here in measuring distance using Cepheid variables has now been tightened down quite a bit. And that's key to getting the Hubble constant right. So let's talk about the early universe. We've already shown you this is the periodic table we get from looking at the various constituents that we see in galaxies, and we can compare that with how nuclear physics, what nuclear physics tells us about creation of heavy elements in stars. And here's what's really interesting. Here's a graph that shows, depending on where you are left to right on this graph, a prediction for the amount of helium we should find in the universe, the amount of an isotope of hydrogen called deuterium, the amount of helium, an isotope of helium called helium-3, and lithium. And this yellow bar, you could slide it to the left or right to try to get to the place where the models, the nuclear physics models, make all these predictions agree with the measurements. So this horizontal bar here is a measurement of helium-3 that we see out in the universe. The green one is deuterium, this brown one is lithium, and so forth. So where would you put this vertical yellow bar that gets all the results close to being correct? And the yellow bar needs to be right here. And the variable you're changing when you're doing this experiment in a computer is how much matter is in the universe. And there's the 4% I mentioned way back early in the first hour of this presentation. The only way to get our nuclear physics model to agree for how much of each of these elements we observe in galaxies is to embrace the idea that 5% of the universe is atomic matter and the rest of it is something else. And for a long time, this was a mystery, but we now know what the other stuff is. And I mentioned it's dark energy, 70%, dark matter, 24%. So we'll go back to this repeatedly and show why we think it's that way. We have a few minutes left. Let me emphasize in those few minutes the idea of this cosmic microwave background. You need a special instrument to see it. It has to be sensitive to microwaves like the ones in your kitchen appliance. And when you look in detail at the sky around you, you see a map like this. And I'll explain next week why the map has this shape. And it turns out the temperature of the microwave background left over from the Big Bang is not uniform. It has warmer areas, these little red areas, and it has cooler areas, the blue areas, and yellow in between. And it turns out a trove of information is captured in this temperature map. There's your microwave, and this is the oldest light in the universe. It comes from a surface around us 45 billion light years away. And it's a history of the map of the temperature in the universe before the universe became, or just as it became, transparent. The temperature variation we're looking at here is incredibly tiny. tiny fraction of a centigrade degree, a fraction of like a few parts in 10,000. But nonetheless, it's there. And it was a big surprise when it was eventually seen. And what it gives us is this. If we look at the amount of matter in the universe and the amount of dark matter, dark energy, and try to overlay all the data we have to get to a single value for where we are in terms of dark energy and matter, we can use the supernova data and the cosmic microwave background data and something called baryon acoustic oscillation. So we produce this concordance map. I call this the celery. That's one way to look at the universe. Here's another way, the caret, and they intersect there with the supernova data. And here, this line tells us the universe is flat, and we get a concordance right there. There's more to this. We can even go deeper and get even a tinier uncertainty by digging deeper, and we find consistently using multiple different independent pieces of science, we find the universe is about 70% dark energy and 30% matter. So we're going to stop here today. Thank you for your attention. Make sure you see, we have one more question. Oh, if we think of the universe as having an outer edge, no, we don't want to do that. So I say to Chris, who asked the question, I'll answer this in more detail next week, but no, we don't want to have an edge. We want to think more about a universe that is a sphere in a higher dimension, and spheres have no edge. So, I will get into this in more detail next time. Thank you for your attention. And we will end our session here, and I'll see you next week.